Yeah, tomorrow in the afternoon.
Are you making the quiz tonight or tomorrow morning?
Tonight. I want to do things ahead of time, so I don't have to do it tomorrow. Okay, so we left off with example B. Now we want to find if it's even or odd. Okay, so if it's even or odd, remember we need to prove the even part first.
Sir, you always have to do first.
The reason why
Just because it's easier.
it's easier because you have this, which you need. You have this already done, and you need that for the odd function. So it's one less step to do.
So you just do even first for
Yeah.
simplicity.
Just for simplicity's sake and time saving's sake. Okay. So the even, we need f of negative x is equal to f of x. So we have 3 negative, and remember we are subbing in negative x or x. So we have negative times negative x minus 1 is equal to f of x. So what is a negative times a negative? Positive. So we get 3 to the x minus 1 is equal to f of x. Is that true?
No.
No, because our original function is 3 to the negative x minus 1. And when we simplified, we got 3x minus 1. So not even. And last but not least, we have to prove the odd part. Okay? So we want to do our odd. We have our f of negative x already. We just need to prove negative f of x. So we're multiplying the whole function by a negative. Okay? So negative 3x, 3 to the negative x, minus 1. When we FOIL in that negative into the bracket, what does it give us?
Negative 3.
And does that equal f of negative x? No. So therefore, it is not odd, and we have no symmetry.
Wait, so does the negative go to the exponent as well?
Nope. Remember, the only time you multiply an exponent is if it's to a power of another exponent. Right? So it's not even, not odd, so there are no symmetries within this function. Okay? Even if you were to slice it down the middle, horizontally rotate it, there's no symmetry. Right? So is everyone getting more comfortable with this whole even odd stuff?
Yeah.
So what's the odd, like, what does odd mean? Like,
Odd means symmetry in terms of if you rotate it, okay, it'll look similar. Okay?
okay.
That's what it means. Even symmetries, if you split it right down the middle, both sides are identical.
Okay.
Right? So like, for example, the parabola, it's a u, you slice it down the middle, it's basically an exponential function on one side and on the other side as well. I think we have one more page after this. I don't know.
Yeah.
So for example 4, we want to determine a parent function that matches the characteristics given. So the function is neither even nor odd, and as x approaches infinity, y approaches positive infinity. So what kind of functions, parent functions, would that be? No, remember we're just looking at x approaches positive infinity. So remember, it has to be a graph that only has, as x approaches the positive infinities, it gets bigger.
Oh, no. Oh, what's the one that's like reciprocal?
No.
No, because that goes from. Oh yeah, it goes to yeah, it goes to 0.
Wait, so that's saying positive to positive?
So what this is saying is, as the x values get bigger, the y values also get bigger.
It's not even or
So look at the current functions on page 1.
So would it be
exponential.
Exponential. But remember, is exponential even or odd? Or is it neither?
So that's positive.
What about parabola?
Parabola is even. The roots? So basically odd and even. So if this were even, if I split it down the middle, you have two identical sets
Like in the middle.
on its axis of symmetry, right? So for example, in the parabola, that would be the vertex, right? That's where it's sliced in half. If you were to slice it in half, like right here, it's not going to look the same. That was even. Even is slicing down the middle.
And then odd.
For odd, the definition was, let me just refresh. So for odd is any function that has a rotational symmetry about the origin. Okay, so if you rotate this, like clockwise, okay, it has to look the same. So because if you rotate this anywhere, it's gonna either be flipped the other way, or it's gonna be flipped the other way as well. Okay, so remember, odd is when you rotate it, it should be symmetrical.
Symmetrical or stay the
Right?
same? Or if you rotate it, would it be symmetrical or stay the same?
It should say the same and be symmetrical at the same time. Okay. So what was an example of an odd function?
The linear one? What was that?
No, that was under.
So 1 over x was odd, right? Correct? So we had 1 over x be odd. We proved that. So if you were to rotate this, it would still look the same, right? Because if you rotate it this way, you're still going to get this, and you're still going to get that. It's just rotated.
And it's like the only one.
There should be another one. Sine x is also a rotational odd function. Okay.
Wait, so
For sine x.
What was the answer? Root
Yeah, root x is one of the answers for that one.
so why is the exponential one an odd one?
Why is it not?
Why is it neither?
Oh, because the exponential from negative infinity, it's always going to positive infinity for the y's.
Oh, so it has to be like that.
Yeah. And as x approaches negative infinity in the exponential, right? Because this is the exponential function. As x approaches negative infinity, it approaches the asymptote, so it approaches 0.
Okay.
So that's why that can be true. So sine is odd because when you rotate it, just think of a wheel. If you rotate it any sort of way, you're still going to get the same way. Okay? So that's why sine x would be considered a odd function.
Like you have to do it by like 180.
Yep.
Like if you make it, like if you rotate it by like flash, you're gonna be upward. So like how does that work? Like,
90.
like you have to rotate it by like.
Hi, Louis.
Yep.
Hi, it's Robinson Resource. How are you? Good. I was assigned to your class as a resource, as a support teacher. I'm in resource. If you want to come and chat with me, is there anything I can do for the class? just let me know. I'm in 213, right? Yeah, but I believe it says class. What other class do you teach? Okay, class. Okay. Take care.
Repeat the question.
Yeah, so like the rules for like rotating, like if you rotate it like a weird way, you know,
For the sine function,
yeah, or like any of them, like you have to rotate it by like,
so it's rotational about the origin.
Yeah.
If you rotate it about the origin, you're still gonna get the same graph. If you keep flipping it, you're still gonna end up with the same graph somewhere. Okay, so let's just say this is our origin. If you keep going, okay, you'll end up with the same graph, okay? On the x-axis, it will just be flipped and it will most likely look the same. So basically, if you rotate this 360 degrees, you'll still give you the same graph. Right?
like I'm just like thinking like if it's like this, it's like a squiggly line.
Oh, you were talking about this?
Yeah, like, if
Yeah.
you rotate it like that, like you have to rotate it so that it's like it can be.
Yeah. So when you rotate it so that if it looks the same, then it has an odd symmetry. Okay? So what other function has a neither or odd and has as x approaches infinity and y approaches positive infinity? And for cohort A and C, it is not linear because as you approach negative infinity for the x's, you approach negative infinity for y. Oh no, Yusuf, you're right. It does hold true because remember when the positive for exponential, when it goes to positive infinity, the y's go where? For exponential. Positive
Wait,
infinity.
what am I right about?
The exponential function is a,
For this thing, right?
yeah.
Okay.
So because it's only giving us the statement as x approaches positive infinity, y approaches positive infinity as well.
Okay.
So for exponential, as it approaches the positive x values, it approaches positive infinity.
Oh, can you also do absolute value?
No.
No, because negative
Oh,
infinity.
damn, I was thinking about positive infinity. Oh, then I forgot.
Yeah, so those would be the only two that would have that as an example. Yeah, because none of the other ones do.
Wait, so is sign included or no?
No, sine is just for,
Oh.
she asked the question, how do we know sine is an odd function?
And like why is absolute?
Oh, because absolute value, we have the V shape. So on the left side, even though the x's are approaching the more negative side, the y values still go up. Because absolute value, even though you have a negative number, the absolute value of that negative number is always positive. Correct?
Yeah, so like isn't that good?
But remember, a absolute value function is what, odd or even? Because we also have to take note of this statement over
Yeah,
here.
that's what I forgot.
Forgot how that works.
So the absolute value is a even function, right? Because if we split it down the middle, it splits in half, okay? And this question is asking us the function is neither even or odd. It would be correct if it didn't have that statement, okay?
And so it doesn't matter that it's like, there's a close point?
Pardon?
It doesn't matter if there's a close point?
Not in this place. It's assuming the function is continuous. Because it says from x approaches positive infinity, y approaches positive.
So unless it states like, oh, you can just assume it's
Continuous.
continuous.
So you have two more examples or one more example? You have two more examples. So the function is odd and continuous. The function has zeros at -3, 0, and 3. The interval of increase is -infinity to -2, or 2 to infinity, and the function is decreasing on the interval of -2 to +2. So what should I start drawing first? What is the easiest thing to draw on this thing, given the information we have? Pardon?
Like a sinus photo?
No. What should I draw first? It's in the second point, second bullet.
Oh,
The X.
I should draw the zeros first.
I think we overthought that.
Well, that's the last one. Two things.
0 and 3. So now we want to look at the intervals of increase and decrease, okay? So meaning the function is continuous, meaning there's no breaks, okay? And odd, meaning it has either an odd exponent, or if you rotate it again, it'll look like the same thing. So let's start with the interval of increase. So where am I increasing from? So remember, this is -3. So -2, because then we have 2. So remember, our interval of increase is from 0 to -2. So that's where I'm increasing from, okay?
Wait, 0 to -2?
Pardon?
It's infinity to -2?
Yeah.
And
So
stop there?
infinity, so -infinity to -2. So we would stop here. Okay? Because that is an interval of increase. Okay? And what happens from -2 to +2? Decreases, right?
Oh, okay. That makes sense.
So from -2 to +2, it decreases. And then what happens at the point 2 to infinity? It increases again. So, you guys learn about turning points in grade 11? For the number of zeros and what it means?
Like, I don't know.
Okay. So, how many zeros does this have? 3. And it has 2 turning points. So, we're going to learn about this in polynomial functions, but because it has 2 turning points and 3 zeros, it is a cubic function. There's one here. And
Oh, the one it drops or increases,
Yep.
essentially.
those are called turning points. And the number of zeros is -3, 0, and 2. Okay? And 3. So I'm just going to do this, just an example of what you guys should expect when it comes to actually writing down the equation of this function. I'm just going to do it fast. I'm not going to explain it yet because I want to explain it in more detail in Unit 3. So essentially what this would look like is x, because we have x is equal to 0, x minus 3, x plus 3. As you can see, we have zeros at -3, +3, 0.
See, if that was like our thinking application, would we have to do the equation?
Find the A.
No, like just.
Oh, no, no, I
It
would,
says sketch a graph.
I would, it would just, because it just says sketch a graph, you just sketch a graph. I just want to show you this to tell you guys what to expect in the polynomial unit. And obviously you would have to go and find A after that.
Sir, so you know how like when we started doing the odd and even, if it's like if like for example we do every single parent function like check whether it's odd or even, it only matters about the exponent or like Like, you know what I mean? Like, it doesn't matter about what the parent function is, because it can be any. Okay.
So is everyone fine with this one? You're just sketching the graph, you don't have to. You're sketching the graph and following the rules that it gives you. Don't forget about the equation. I just wanted to show you this.
So essentially, we're just given the property that we just have to sketch.
Yeah. So, like I said, map out your zeros first. You know there's an interval of increase from negative infinity to where x is negative 2. And then it decreases from x is negative 2 to x is positive 2. And then increases again from 2 to infinity. Oh, look, we're at the last example for 1.3.
Yay.
The next lesson is easy. You guys, I'm pretty sure you guys are pretty familiar with transformations, right?
Pretty sure. Use that equation, right?
Ax or whatever is c, x plus b
Yeah.
squared plus c.
I think that's the-
So when one of the parent functions is transformed, it yields a graph with these characteristics. So you have the domain is x is an element of all real numbers. We have r is y is element of real numbers such that y is greater than 3. As x approaches the negative infinity values, y approaches positive 3. What is the equation of the transformed function? So first of all, just based off those characteristics that we were given, is there an asymptote somewhere? Okay, where would it be?
3.
At y equals 3. Okay, so I want you to look in your parent functions. Tell me the parent functions that have asymptotes for it.
Reciprocal and exponential.
So we have reciprocal and the exponential, right? So now we need to determine, based off our knowledge, which one of these would it be?
Exponential.
Okay, why would it be exponential?
Because if it was reciprocal, it would be like, it cannot equal. But like, since it's not, then it said like greater than.
Perfect. So as x approaches negative infinity, that means the left side of the graph is going to be going this way, and then the other half is going to be going up. Okay, because that's how the exponential function works.
Wait, what? Wait, so x, so like we have to look at each coordinate like by itself, like, so like x is negative.
So
infinity.
as x approaches the negative numbers on the left side, the graph approaches 3. That's where the exponent is.
So then, why wouldn't it just go up?
It would go up. So from left to right, it keeps going up.
Oh, okay, okay.
So, but just for this specific side, we have to look at this specific characteristic. Okay? Because as x approaches the negative x values, the y value approaches 3 for the exponential function.
That means x approaches positive 30. Y approaches positive 30.
Yep.
Okay.
Good job. So, and we can say as x approaches positive infinity, y approaches positive infinity because it keeps going up. Yeah.
So like, if it was in, like, I'm just using this as an example because like it's just confusing me. Like, if it's, if x is positive infinity and y is negative 3, how would it look on the graph?
So you're saying, so this is just an extra example. So you're saying if x approaches what? Positive infinity?
Yeah,
And y approaches what?
negative 3. And it's like this same
The
function.
same function? It's just flipped.
But isn't that a decrease then?
We're just looking at end behaviors. We're not looking at interval of increase or decrease.
Oh, okay, okay, okay.
Sorry, I'm still quite confused on x. So as x approaches negative infinity, y approaches 3. Well, if you're reading the graph from left to right exponential, then wouldn't that technically go?
So remember, n behaviors, you're looking at the arrows at the end of the graph, okay?
Yeah.
And the intervals of increase and decrease, you're looking at the domain.
Oh.
So we're reading this as x approaches all the negative numbers possible on the left side of the graph. Y approaches positive 3. Okay? So as x keeps getting more negative and more negative, the exponential function is getting closer and closer to 3, but not actually hitting 3.
Oh, so it's only describing that
Yeah,
one half.
yeah.
Okay.
So, and Yusuf described the other half, or Joseph, sorry, where x approaches the positive x's, the y keeps going to positive infinity.
So if you were given, so say for example, it described one half of the graph, it would still, that graph would still work.
Yeah.
Oh,
It would work.
oh,
So the equation of our transform function would be f of x is equal to 2x. And because it moved up 3 units, what would we be adding or subtracting at the end of that equation? Plus 3. So you guys will get more practice with the homework. You guys can always ask me questions on Google Classroom or before class. I know you guys can't usually come in as early as before. So you guys have to come in at 8:05. Who here used to come to school at like 7:50?
Yeah, bus.
What's yours?
We all take the bus?
You guys don't take the bus?
What?
Yeah, it's cool. Oh, yeah, you drop us off
And one day he's like, sorry.
Okay, so that was it for the characteristics of functions. So remember, key things to note for n behaviors, you're just looking at where the graph is heading in the positive x-axis and the negative x-axis. And for the intervals of increase and decrease, you're just looking at the x values, okay, the domain. So what we're going to do next is, it should be short, it's the transformations of graphs. All right, so let's start with an easy warm-up. So we want to match the graph with the equation. So for number 1, what equation does it correspond with? E. So this is E. For graph number 2, which one does it correspond with?
C.
C. For graph 3, which equation? F. And last but not least, graph 4. E. So obviously, these are the parent functions, but obviously the graphs have been transformed, and that's what we're going to look at for this lesson. So we have our equation, which is at the top over here. So the function can be transformed in the form of y is equal to a, f of k times x minus d plus c can be graphed by applying the appropriate transformations to the parent function y of x, where a vertical stretch or compression factor, if a is less than 0, is also a reflection in the x-axis, okay? So if a is bigger than 1, do we have a stretch or compression? Stretch. Has been stretched by a factor of a. Okay, and if it's less than 1, compression has been compressed. And like it said on the top, if we have a negative in front of the a, it is going to be reflected in the x-axis, okay?
So all negatives are compressed?
Not all negatives are compressed.
Because it said that if A is less than 1.
If the absolute value of A is less than 1.
So, like, what's an example? Like what?
1/2.
Oh, like fractions?
Yeah, fractions.
Okay.
Because the absolute value of -3 is 3.
Okay.
That's bigger than absolute value of A. So if you have negative, it implies a reflection in the x-axis. So we have a horizontal stretch or compression by a factor. If k is less than 0, there is a reflection in the y-axis. So if the absolute value of k, like the ones in the brackets get most people confused. If the absolute value of k is greater than 1, the parent function is what? Compressed or stretched?
Compressed?
Yep, it is compressed. Whatever you see in the bracket is the opposite.
Horizontal, that's
Compressed horizontally, 1/k. So if absolute value of k is less than 1, if it's a fraction, is it compressed or stretched?
Correct.
Stretched. So remember, it's the opposite.
So we always have to flip it when you say, right?
Yep.
But that's only for the K?
That's only for the k.
Okay.
Whatever is in the bracket is the opposite of what you think it actually is.
Wait. Both of them said 1/k.
So when you divide, so if you have, so let's just say, for example, let's just say k is 1/2. Okay? So what's 1 divided by 1/2? It's just 2. Right? Because you're just going to take 1 times 2/1, which equals 2.
Now you lost me.
Like 1 divided by.
I don't think he's just.
So-
I'm just confused about like,
The rule.
so when do I have to like switch it? Like what's the rule of like switching it? Like if
So-
I see like 7/k in the actual equation,
Mhm.
would that be
Well, it's not gonna say 7/k in the equation, it's just gonna say 7x. Okay?
Now you're taking.
So and that would be your k value, okay? So let's just say our k is, let's just say 7, okay? Remember, we have this, it's compressed or stretched by 1/k, all right? So because our k value is 7, we got 1/k is equal to absolute value of 1/7 because k is 7. And what's the absolute value of 1/7? 1/7.
and that would be compression? Okay. But then if it's
But then if you have a fraction, let's just say, give me a fraction.
like 1/2.
Okay, let's just say k
1/4.
is equal to 1/4. Okay? So if k is equal to 1/4, we still have to follow this definition. Okay? So we have absolute value of 1/k, or if you don't want to confuse yourself, or it's the absolute value of 1 divided by k. Right? It's the same thing, it's just a different notation. Some people prefer this one because they don't like seeing numbers stacked on top of other numbers. Okay? And that's what messes up people's minds. So for our sake, let's go with this one. So we have 1, absolute value of 1 divided by 1/4. And when we divide fractions, what do we do with the second fraction? We flip it, right? And it becomes multiplication. And what is 1 times 4/1? 4. And what's the absolute value of 4? Yep, and that would be a stretch.
Okay.
So when it's saying if absolute value of k is greater than 1, that means the initial value of k before you input it into 1/k.
So this is already, if k is less than 1, which this is the case, is a stretch.
Okay.
What we took before, if k is equal to 7, that is greater than 1, it is a compression.
But yours is semester weight.
So are you?
I'm good, that makes sense.
Thank you, sir.
Trust me, guys. And a lot of people get these questions wrong in transformations. It's like, oh, it's a stretch of 2, but it's actually 1. Okay, so we have D. So D is the horizontal translation or shift. So if D is greater than 0, then the parent function has been what? Translated to the
Right?
right? But what does it have to appear in the brackets as?
Negative.
Yeah. So the bracket has to be negative. Okay, so it would look something like this. So let's have f of x is equal to x minus 3. Okay, so that's how it would have to look inside the bracket.
But like if we do like all the like if you put all the letters and you say like, oh, tell me what it is, we have to say positive.
Pardon?
Like what my teacher did last year was like she just gave us like all the questions and stuff, and she's like, what's A, K, D,
Okay.
whatever. So in that case, would I have to put -3 still, or do I just flip it to 3 or?
You would move it to 3.
Okay.
Because once you take that out of the bracket and you isolate the x, you get what? Positive or negative 3.
Positive.
Positive 3, and positive always corresponds to going to the right.
Okay.
Okay? And then if d is less than 0, then the parent function has been translated what? Okay? And that means the bracket has to be added on the inside. Okay? So the horizontal stuff is the more complicated stuff. Not the more complicated, it's the, I guess, the more confusing out of the two. Because for the vertical stuff, you just take it for what it is. Okay? So for example, C is vertical translation or shift. So if C is bigger than 0, then the parent function has been translated what? Up or down? Up. And if it is less than 0, translated down. I got 7 more minutes before Baxter the dog starts barking at us. We're just going to do a couple of examples. That's all it is. Okay, so we're just going to be doing these examples of, and then we'll do one mapping notation example, which you guys do mapping notation.
Like transformation maps?
Yeah. Okay. I don't know how they taught you. They use the formula.
Yeah, they use the x over k plus or minus.
Perfect. Okay, so we're going to describe the transformations that would be applied to y is equal to f of x. So you have y is equal to f of x minus 2. What kind of transformation do we have? Yep, translated 2 units down. Okay, for B, do we have to do anything first before? Yes, we're going to factor 1 over 4.
Oh yeah, I'm gonna forget about that.
So remember the. So what is it? 1 over 4 bracket x, and then what? Minus 8. So here we have 2 transformations. Okay, what's the first one?
Translation to the right.
Okay, no one wants to say the hard one because they're going to get confused.
Oh, and it's.
Say
I
it.
see what it said. It's like it's gonna be like the opposite, so it's gonna like stretch by a factor of.
Yep.
1 over 4. 4.
Okay.
Yeah.
Okay.
Yeah.
Okay, I get it. Oh,
Horizontal stretch of 4.
It's the opposite of what you think it is.
Yeah, it's almost always out.
That's the only thing you're not going to ever have to think about the opposite in math. It's just this.
It's just counterintuitive.
So the next one we have C. we have y is equal to negative 1 over 2, f times x minus 3. So we have 1, 2, and 3 transformations here.
Reflection in the x-axis.
Yep.
And then vertical compression of 1 over 2.
Yep.
And then translated three spaces to the right.
Damn, you got it all right.
Why are you so sharp?
I'm not sure. Because you were doubting yourself before.
Yeah, that's true.
I have a quick question. Why was mine special order, but then this one's just a half?
Because.
Oh, because this is in the y, it's outside the bracket.
That's
Oh,
the
okay.
value.
So anything outside the bracket corresponds to the y's. Okay, so your vertical stuff. Anything inside the bracket corresponds to the horizontal compression, stretches, and shifts.
Okay.
So the last one we have all 4. Okay. So what would the first one be?
It's a stretch of 3 vertical.
Vertical stretch of factor 3. Anything else? Oh, Joseph.
Horizontal compression.
Not negative half,
Or just half.
just half. What does the negative stand for?
Reflection the x.
Other one.
Y.
Yeah. What else? Okay.
Up. Oh, sorry, down 4. My bad.
And what's the last one?
Oh.
Translated to the left.
Yep. So this would be an example of a communication question. Okay.
Well, I think that's probably.
Because for one, you're stretching out the x values, so although the y values are getting, the x values are getting smaller, the output in the y is getting bigger. So it's getting stretched on just like a rubber band. So if it were compressing the y, the graph is getting fatter. Okay? Because you're basically, the output's getting smaller for the x's. So let's do one mapping notation question. And then we are probably good to go. So we'll skip A. We'll do, oh, you guys try accessing the website for Gonzaga Math? It works?
Yeah.
Works?
It works. Okay.
So we have y is equal to negative 1/2 x minus 1. So when we start these questions, let's start with graphing the parent function. What is the parent function of this transformed graph?
Y for f of x equals square root of x.
Okay? And just give me the first few points for this graph.
Like just random point.
Well, what are the major points in the graph root x?
Oh, I remember this. I just forgot. 0, 0. No, I actually have no idea.
What's the square root of 1?
Oh, so you just okay, yeah, 1, and then
What's the square root of 4?
maybe 2 and then 4.
4, 2. Because you don't have a perfect square root of 2. So I just skip to the numbers that have a perfect square root. So it makes it easier
Oh,
to
okay.
graph. So you have 0, 0, you have 1, 1, and you have 4 and 2. So this would be your parent function, okay? So what type of transformations do we have for negative 1 over 2x minus 1?
A reflection in the x-axis.
Okay. What else?
You got a factor of the k, so it would be I don't know how to do math. 1, 2, yeah. So it would be a stretch of 2 horizontally.
Yep. Horizontal stretch of 2,
And then right 2.
and then 2 units right. So with the mapping notation, okay, so whenever x and y, which remains unchanged, okay, that was a very big bracket. And we're going to transform it to what? So we need to look at the x's, okay? So how are the x's transformed?
Translated to the right.
To the right, and was there a horizontal stretch or compression?
Stretch.
Stretch, right? So it'd be 2x plus 2. And did we do anything with the y's?
Be reflected.
So we're multiplying the y's by
Negative.
negative.
What's the mapping again? Like x.
So all you're doing is looking at the transformations, okay, and determining an algebraic expression for them.
I know, but wasn't there like some mapping formula that was?
Yeah, so it's the mapping formula is this. So mapping notation. So x comma y goes to, we have x over k plus d, and then ay plus c. That is our mapping notation. So in this case, our k was 1 over 2, okay? So you have x divided by 1 over 2, it just becomes 2x, okay? So k is equal to 1 over 2. So we have x over k, x over 1 over 2, which is equal to 2x.
Oh, we wouldn't put the 2 as k.
Pardon?
Like, didn't we already switch it? Like, say, like horizontal stretch of 2.
Yeah, no, but I'm just giving you an example to sub it in for the mapping.
Yeah, I know. So like, why wasn't we sub in the 2 for them?
Because our 2 is not our k. 1 over 2 is our k.
Okay, okay. So then for the d, would we put -2 or +2?
For the d, we would put +2. Because once you take this out of the bracket, it becomes a positive number.
Okay, so the k doesn't change when you put it in mapping, but everything.
Yeah.
Okay.
So our mapping is 2x plus 2 for the x's and -y for the y's. Okay? So we have our point 0, 0, 1 and 1, 4 and 2. So using our mapping notation, what do these transformed coordinates turn into? So if we sub in 0 for x, we get 2 times 0 plus 2, which gives us 2. And then 0. If we sub in 1 for x, what is our x value for x coordinate? So 2 times 1 plus 2 is 4. And what is our y value? -1. And if we sub in 4 for x, what is our x coordinate? 2 times 4 plus 2. 10. And what is our y value? -2.
Hold up. You did 2 times 4? I mean, 2 times, yeah, you did 2 times 4?
Because the x value is, for the third point, is 4, right? So you would multiply 2
Yep.
with 4 and then add 2, which.
So you're taking all the x values from your parent function and plugging them into the mapping notation for the x's.
But I thought the k was 1 over 2.
Pardon?
I thought the k was
Yeah,
1 over 2.
Yeah, but you get rid of the k when you have the number already for it.
But what you said, like, just to keep as a fraction.
Oh, just like for your base notation. That's what I want you to do.
Nah, you lost.
So this is just the general formula for mapping notation.
Okay.
Okay? Once you plug in the value for k, the k goes away.
Sorry.
So once you put in the number for k, your k goes away.
Okay.
So So you're just left with a number multiplied by x. So in this case, we were left with 2x plus 2.
Okay. Yeah, I get it.
Right? So what you would do next is just plot the points, and then you get your graph. Yeah, so tomorrow you have a quiz on 1.1 and 1 to 1.4. It'll just be multiple choice, basic knowledge questions, and you guys should be fine. So cohort A and C, you guys can log off. For those of you who want the textbook, just check the school Twitter or their websites, and you guys can pick it up probably this week.